In this video, we're going to look at vector-valued functions. They're also known as vector functions. If we have time, we'll also look at graphing plane curves that are given by vector-valued functions. And we'll look at graphing space curves given by vector-valued functions. And probably in the next video, we'll look at the domain of vector-valued functions. We'll discuss whether or not a vector-valued function produces a smooth curve, and we'll talk about limits of vector-valued functions. So you might say, okay, well, what is this thing, a vector-valued function? Well, I think it's helpful to compare them to functions that you're already familiar with. So we've studied, back in pre-calculus or college algebra, we've studied functions like this. Something like f of x equals x squared. What this function does is it takes a real number, and the domain is all real numbers here, and then it maps it to some subset of the real numbers. So it's mapping it to, well, this x squared takes on values of 0 all the way to positive infinity. So it's mapping it to this interval from 0 to infinity, which is a subset of the real line. So basically this function takes a real number and it gives you a real number. If I give you an x, you're going to give me an x squared. So if I give you a 2, if we're using this mapping, you're going to give me a 2 squared back, which is a 4. Or if I give you a negative 3, then you're going to give me a negative 3 squared back, which is a 9. So we're used to functions like this. They map real numbers to real numbers. They're taking some element in the domain of this function, some real number in the domain, and mapping it to an element in the range. Now, vector-valued functions are very similar. And they're denoted by a vector, r of t. T is a real number. And if we are in 2D, we could define a vector-valued function this way. X of t times I hat plus y of t times j hat. Or I prefer the shorter notation, x of t times I hat plus y of t times j hat. And what this is doing is it's taking a real number t from the domain of R, which is just some subset of the real line, and it's mapping it to a vector in two-dimensional space. Now we're not going to think of it as mapping to the entire vector, but we're going to think of it as mapping to an output, a single point, x of t, y of t. So if we're just looking at the end point of this vector, this is mapping to 2D. Or we could have a vector-valued function r of t with 3 components, x of t, y of t, and z of t. And I would probably write it like this instead because it's shorter. But again, r is just going to take a real number, give me a number t. In the domain of the function, we'll talk about how to find the domain in a little bit, which is just a real number, and it's going to map it. And it's actually giving me an output of a vector, but I'm not going to look at the whole vector, I'm just going to look at the end point of the vector. So it's mapping to R3. So another way that we could write this is we could say it's taking this real number t and it's mapping it to a point, x of t, y of t, z of t. Now these functions, x of t, y of t, they're familiar functions. These are functions just like this. You give me a t, and this will give you an x. You give me a t, this will give you a y. So this is just a real valued function, just like we talked about in pre-calculus. So is z of t. All of these guys are just giving me real numbers back. But r of t is a vector. And this vector r of t points to a particular point. If we're in 3D, it points to x of t, y of t, z of t. If we're in 2D, R of t starts at a number t, and it points to a point x of t, y of t. Okay. Now, if I think of this as pointing to a position in space or a position in the plane, we can think of these as representing position vectors, giving you a position, x of t, y of t, or x of t, y of t, z of t, at a particular time t. Now, t doesn't have to represent time. It can be just some parameter, some third or some fourth variable here. And as t increases, we're going to get an x, a y, and a z for every t. But I think it's very helpful to think of it this way. At a particular time, we're going to be at a certain location, and r of t is going to give you that location. Now, r of t itself is a vector that points to that location. It's sort of saying, you are here. This is where you are. It's going to start at the origin and point to this location. So let me give you an example. And in our examples, we're going to start graphing some curves in the plane and in space. If r of t is a vector valued function with two components, x of t and y of t, this is going to give us what's called a plane curve because it lives in two-dimensional space. Or if r of t has components x of t, y of t, and z of t, it's giving us a space curve because it lives in three-dimensional space. So let's look at a couple of very simple examples. Let's start here. Okay. Now I've got x of t equals t squared times I hat plus t times j hat. And remember what's implied by this. It's implied that x of t equals t squared and y of t equals t, just from the order that those components are listed. X of t and y of t are called the parametric equations of the vector valued, or the parametric equations of the curve C. They're also the components of the vector valued function r of t. Now, if I want to graph this curve, one thing that we typically do is we eliminate the parameter t. So we're trying to get rid of the t here and just find a relationship between the x and the y so that we can graph it the same way that we graphed y is a function of x or x is a function of y back in pre-calculus or algebra class. So it's actually pretty simple with this one. If y equals t and x equals t squared, I can put those together. I'm going to drop the dependence on t. Well, I can replace this t with a y. And so we get x equals y squared. Hopefully you remember that's a parabola on its side. And that's going to be our plane curve. We're going to call it C. And I'm going to say that it's generated by r of t, which has components x of t and y of t. So those parametric equations x of t and y of t, and this collection of points C that we're about to graph, all of those together form the plane curve. So let's just plot some points on x equals y squared. When x equals 0, y equals 0. If you're not sure, you can always make a chart like this. When y equals 1, x equals 1 squared. When y equals -1, x equals -1 squared, which is also 1. When y equals 2, x equals 2 squared, which is 4. So I'm plotting the point 4, 2. And when y equals negative 2, x equals negative 2 squared. Negative 2 times negative 2 is positive 4 as well. And so we get this. So this is the curve. Now I'm not going to draw arrows on it because the arrows mean something in this class. Since we weren't given any restriction on t, we are talking about the entire parabola. But the parametrization, this choice of x of t and y of t that gave us this collection of points, induces an orientation on the curve. To figure out the orientation, I need to think about which way this curve is traced out as t increases. So let's say when t equals negative 2, let me put this on my chart. When t equals negative 2, that's when y equals negative 2. So we're at the point x equals 4, y equals negative 2, and that's when t equals negative 2. So we're right here. And when t equals negative 1, that's when y equals negative 1, and x equals positive 1. So we're there. And when t equals 0, y equals 0, because y and t are the same thing, and x equals 0. So it looks like as t increases, we're going t equals negative 2, t equals negative 1, t equals 0, t equals 1, t equals 2. So this could be the path that some object is traveling along in two-dimensional space in the plane. And this could be the time that that particle is at that location. So in general, this is just a point x of t, y of t, and its components are given by the equations t squared and t. But as t increases, we're going this way. As t increases, y increases. So this is the orientation of the curve. The arrows indicate the orientation. As t increases, we go here. And you might have said, okay, Miss Townsend, I saw you plot some points. I saw you graph x equals y squared, but I don't see any vectors r of t. And you're absolutely right. I didn't draw any vectors r of t. Remember what I said before. R of t is taking a number t in the domain of this function, which happens to be all real numbers. So I can put in any t value and I get any x and y values I want out of that, or the appropriate x and y values given those equations. So I put in any t value and I get a single point. We're thinking of this as mapping to a point, x of t, y of t, which in this case is given by t squared and t. So we're mapping to this point. But if I want to sketch r of negative 2 and r of negative 1 and r of 0 and r of 1 and r of 2, well, those are vectors. Let me put this together for you. T and y are the same, so I'm just going to fill that in. So r of 0, that has components x of 0, y of 0. So it's actually a pretty boring vector. It's just the 0 vector, 0, 0. Now when I substitute in t equals 1, I get x of 1, y of 1, and that's 1 squared and 1, so I just end up at 1, 1. So r of 1 is actually the vector that goes 1 unit in the x direction and 1 unit in the y direction. Usually we have its initial point at the origin. So r of 1 is the vector that points from there to there. It's a little bit hard to see, but that's r of 1. And then r of 2, that's x of 2, y of 2. When y is 2, x is 2 squared, which is 4. So this is the vector that starts at the origin and points to the location x equals 4, y equals 2. So here is r of 2. And that's t equals negative 2. That's the location there. So that's r of negative 2. We generally don't draw these vectors. These vectors just tell you where you're located. Again, this is just like a pointer, like when you go to the mall and you see that little map and it says, you are here. This is what it's telling you. It's saying, you are here at this location. In general, let me draw a different picture that doesn't have so many vectors all over it. Our curve looks like this, just in general. So we've got this parabola on its side. And R of t points to a location. That's R of t. And that location is given by the point x of t, y of t. And it has coordinates t squared and t. So R of t is saying at time t, you are at this location. And as t increases, we go this way. And that is indicating the orientation of the curve. I said before that this curve is actually defined by two things. The curve is not just this collection of points. It's not x equals y squared. The plane curve consists of two parts. One part of it is the collection of points. That are on this curve. And another characteristic of the plane curve C is the components of R of t, or the parametric equations of the curve. So the plane curve is not just the points, but it's also the equations x of t and y of t that generated that curve. So here are a couple of other vector valued functions that generate very similar curves to the other one. Notice I've got x equals t squared, y equals negative t here for R2. Now if I take negative t and square it, negative t times negative t is positive t squared. So this is also given by x equals y squared. This is my x, it's my x component. This is my y. So r sub 2 of t, this is just another parametric, or another vector valued function. It looks like this. This time I'm not going to draw all the vectors that point to where you're located, but the same idea holds. But this time, for r2 of t, let's plot some points. We'll do t, and then we'll see what x of t is. We'll look at what y of t is. And then we'll look at the vector r of t. So let's put in t equals negative 2. Well, then x is negative 2 squared. Negative 2 times negative 2 is positive 4. And for y of t is a negative 2. So y is 2. So r of t is 4, 2. So we're at a particular location. R of t is starting at the origin and pointing to x equals 4, y equals 2. So this one's not to scale. So it didn't do as good a job with this graph. So we're right here at t equals negative 2. And then at t equals negative 1, x of t is negative 1 squared, which is 1, and y is negative 1, which is 1. So r of t has components x of t, y of t. Oops, this time I put in a t, I should have put in a negative 2. On this one, I'm putting in t equals negative 1, so r of negative 1 is x of negative 1, y of negative 1, which happen to be 1, 1. So when x is 1, y is 1, we're right here at t equals negative 1. At t equals 0, we have 0 squared, which is 0, a negative 0, opposite of 0 is 0. So r of 0 is 0, 0. And when t is 1, we have got 1 squared, which is 1, and negative 1. So r of 1 is 1, negative 1. Do you see what happened? T equals 2, we're here. 2 squared is 4, and then we've got negative 2. So x is 4 and y is negative 2. It's the same curve as before. I did a better job with my graph up there, but it's exactly the same, not curve, but the same collection of points. But the orientation is different this time. For our t, as t increases, instead of going up, as t increases, the y's go up on this graph. As t increases on this one, y decreases. The y's are going down. So we're traveling this way along the path if we're thinking of this as the trajectory of some object. So this is r sub 2 of t, or the curve generated by r sub 2 of t. So the curve includes both this collection of points that we're drawing and the orientation and the parametric equations. Like all of that comes into play when you're talking about a curve. So even though this curve and this curve are technically the same collection of points, because they have different parametric equations, they are not the same curve. Now this one's also very similar. I've run out of space. I don't have space for this one on here, but I'll put that on the next page. If r sub 3 of t is this, so x of t is t, y of t is the square root of t. So those are the parametric equations of our curve. Now, putting these two pieces together, I can replace x with t. X and t are the same thing. So this is y equals the positive square root of x. Because I'm replacing that t with x. I'm just plugging that in. Now, if you want, you could rearrange this equation. If I square both sides, I get x equals y squared. Oops. That looks like the same curve as what we have right here, but it's not. It's not exactly, because we got to think about some things. On this, t could be any real number. If t can be any real number, we get x equals y squared for every possible value of y. So that means we get this whole parabola. The same was true here with r sub 2 of t. Here's r sub 2. And its graph, or its sketch. It does not matter what t is. T can be any real number. Y is going to be the opposite of that. So the domain of this function is all real numbers because I can put in any t value I want. Everything makes sense. I'm able to get an x and y value out. So the domain is all real numbers. Do you see how this is different? I've got a square root here. Remember from your pre-calculus days, you cannot take a square root of a negative number, not in this class. In this class, we're only dealing with real numbers. I could take the square root of negative 4. I'd get 2i. But I don't want any complex numbers, not in my class, not in this calculus of real variables. The domain of this is not all real numbers. We're restricted. T has to be greater than or equal to 0. Since t is greater than or equal to 0, so the domain of r sub 3 of t is the set of all t such that t is greater than or equal to 0, which is just 0 to infinity. Rather than using this version, I'd like to use this version. These two are equivalent, but I made a mistake there. They're only equivalent in some cases. These are equivalent as long as x is greater than or equal to 0. This, with that restriction, is the same as that. Okay, so let's sketch this curve now. You can make a little chart. Here's t, here's x, here's y. Now, I don't want to put in negative numbers for t this time, but I'll start with t equals 0. 1. Let's use 4 because we're going to take the square root of it. And 9, we're going to take the square root of that. So x is just t, so we get 0, 1, 4, 9. Y is the square root of t, so we have square root of 0, which is 0, square root of 1, which is 1, square root of 4, which is 2, square root of 9, which is 3. And then we can plot some points. So what we're going to see is this y equals the square root of x graph that we're familiar with already just from our pre-calc days. Zero, 0, and 1, 1, and x equals 4, y equals 2. X equals 9, y equals 3. So that's our curve. And notice that as t increases, x increases, and as t increases, y increases. So we're tracing it out that way. T equals 0, we're at this location. T equals 1, we're at that location. T equals 4, we're at that location. T equals 9, we're at this location. So you could think of this as representing time if you want. You could say at t equals 0, we're here. And then 1 second later, we're here. And 4 seconds after we started, we're here. And 9 seconds after we started, we're there. And we get this curve. And we add these arrows to indicate orientation. That looks a lot like this one, but it's the top half only. This one is defined for all real numbers, and this vector valued function is defined whenever the square root is well defined in the reals. So t has to be greater than or equal to 0. Now there are other curves. I've drawn 3 versions of a very similar curve. So let's look at a couple more. So let's say that r of t equals, let's say sine of t and actually, let's do sine of t squared and t squared. I'd say, ooh, how does that get traced out? Well, it's actually, well, maybe that might be a little too much for this class. Let's just stick to sine of t and t. So this is my x of t, and this is my y of t. And we want to put those two together. Now I'm writing it explicitly that x depends on t, y depends on t. So we're using that function notation. Instead of f of x, I'm saying x of t, y of t. This is not multiplication. This is function notation. Now I can put these two pieces together, and I can replace this t with y, because y and t are the same thing according to this. So I've got x equals sine of y, and that's just a sine wave on its side, because we've switched the rules of x and y, but we haven't made any issues about the domain. Y can still be any real number. And I can take the sign of any real number to get a different real number between -1 and 1. So all this is going to work out just fine. So let's see what this would look like. Well, we know first of all that sine is always going to give us numbers between -1 and 1. So the x values on this curve are between -1 and 1. Then we're just going to graph a sine wave. It's going to look a little different because y is our dependent variable, or excuse me, our independent variable, and x depends on y. So it's going to look like I've got a sine wave, but I've reflected it like this way. We know sine looks like this. It starts at 0 and then it goes up. But now we're saying it starts at 0, 0, and then it's going to go up as y increases. So it's a little bit of a reflection. It's a reflection two ways. You might say, oh, Miss Townsend, I'm really not sure about that. I'm going to graph it, and then we can plot some points and talk about where those are in the graph. So at sine of 0 is 0. Sine of pi over 2 is 1. Sine of pi is 0. Sine of 3 pi over 2, that's negative 1. And sine of 2 pi is 0. So it looks like this. And we know sine repeats. I'm trying to do the best I can, draw this graph. So that's 2 pi, that's 4 pi, that's 3 pi, and so on. And we can go back this way. Okay, so that's my graph. I didn't do a very good job drawing a perfect sine wave, but you get the idea. As y takes on different values, x is going to take on some value between negative 1 and 1. So we just get that sine wave on its side. Now we have to think about what happens as t increases. Are we going up or are we going down? Well, as t increases, y goes up. So we're going to go this way. And if you don't really believe me, if you're like, I don't know, Miss Townsend, you can plot some points. I would recommend using multiples of pi over 2 or maybe pi over 4 if you prefer, if you want to be more precise. I would start with t equals negative 2 pi, then negative 3 pi over 2, negative pi over 2, and 0. And then just go on the other side, pi over 2, pi, 3 pi over 2, 2 pi. And you keep going. Now I'm going to leave some space for x. Y is simple, y is just t. So y is going to have exactly the same values that t had. I'll just write those down again. And x has values of sine of t. So we've got sine of negative 2 pi, which we know to be 0. So when x is 0, or one time when x is 0, y is negative 2 pi. So this is negative pi, that's negative 2 pi. So this point is right there. This is where t is equal to negative 2 pi. And that makes sense because y and t are the same thing. Then when t equals negative 3 pi over 2, sine is going to be 1. And so we're right here. And at pi, or negative pi, we get 0. So we're there. And at negative pi over 2, we get negative 1. So we're there. And then sine of 0 is 0. So we're there. Sine of pi over 2, that's 1, we're here. And we just keep going like this along the curve. Okay. Alright, so that is another example of a plane curve. What I've just done, where I got rid of the variable t, is called eliminating the parameter. T is a third variable. It's not shown on the axis except through these arrows that indicate orientation. You see the x, you see the y, but there's no t-axis here. Now it looks like there's a t-axis here, but there's only a t-axis because y and t are the same thing. Okay, so that's how we graph plane curves. Here's another example of a plane curve where it's not as easy to eliminate the parameter t. So let's say you've got r of t equals 2 sine of t and 3 cosine of t. And maybe this time they give us a restriction on t. Maybe they tell us, we're talking about the path that's traced out as t ranges from 0 to pi. Say, okay, we don't get the whole thing, we get part of it. Well, just like before, the first component is x of t, the second component is y of t. Now this time I do not want to solve one of them for t and plug it into the other one, because you see what would happen. If I solve this for t, I would get, well, first divide by 2, and then to get rid of the sign I'd have to take the inverse sign, and then I'm going to substitute this in for t in this function. So y equals 3 times cosine of t, so you have 3 cosine of the arcsine of x over 2. That's not what I want. Yes, it's technically correct. I have eliminated the parameter t, but do I have any idea what that looks like just from looking at this? When I see that equation, I don't know how to graph it. Most people don't. So instead of doing this, we're going to do something else that will allow us to graph this curve. Notice how we've got a sine and a cosine. Anytime you've got parametric equations involving sine and cosine, chances are you're supposed to use that Pythagorean identity that relates sine to cosine. Remember, sine and cosine were on the unit circle? We had cosine of theta, sine of theta. We said if they're on the unit circle, x squared plus y squared equals 1. So cosine squared theta plus sine squared theta equals 1. Usually it's written the other way. Sine squared of some angle plus cosine squared of the same angle equals 1. According to the Pythagorean theorem, using this point on the unit circle, we get this Pythagorean identity. This is what we're going to use to get rid of the parameter t. This works technically, but it doesn't allow me to graph it. So I'm not going to use that. Even though it gets rid of t, I'm going to use this instead. And say, how do we use that instead? It's actually pretty easy. This has a sine in it and a cosine in it. This has a sine in it and a cosine in it. So we're just going to solve this one for sine of t. We're going to solve this one for cosine. And then we're going to square them both and add them together and say that their result is equal to 1. Okay. So let's do that. Rather than doing this, we're going to solve for sine of t. So if I'm getting sine of t by itself, I get sine of t equals x divided by 2. Here, if I'm solving for cosine of t, I get cosine of t equals y divided by 3, because I'm getting that 3 on the other side. Okay, well, sine squared plus cosine squared has to be 1. So here's my sine of t, squaring it. Then we're going to add cosine of t, which is y over 3, and we're squaring that. Sine squared plus cosine squared is 1. And this is playing the role of sine of t. And this is playing the role of cosine of t. They're the same thing according to our parametric equations. So you might say to yourself, what is that? Well, we've looked at a lot of conics whenever we were graphing our quadric surfaces. I hope you recognize it. If I square the numerator and the denominator, I end up with x squared over 4 plus y squared over 9 equals 1. And that's an ellipse centered at the origin. I can rewrite that this way with perfect squares in the denominator. Makes it just a little bit easier to graph. If I'm graphing the ellipse, not the curve given by the parametric equations or the vector valued function, but just the ellipse, I start at 0, 0. Since there's a 2 squared under the x, we're going to go plus and minus 2 units in the x direction. And because there's a 3 squared under the y, starting at our center, we're going to go plus and minus 3 units in the y direction. And those 4 points are on our ellipse. and it looks like this. You might say, okay, Miss Townsend, I'm done. Let's just put some arrows on there and be finished with it. Well, we're not quite yet done. This was the set of parametric equations. We were given x is 2 sine of t, y is 3 cosine of t. R is the point that goes from the origin to that point on the ellipse, and it says you are right here at this particular time. And t ranges from 0 to pi. So we're going to say, if we have t going from negative infinity to infinity, I'm sure we would trace this ellipse out multiple times. But we only get part of the ellipse. We might get the whole ellipse. Maybe we trace it out exactly once. Maybe not. So to figure out what part of the ellipse we get, let's just plot some points. Always a good idea. If we're not sure, this will always work. So let's use 0, and I want to use pi as well. Then just pick some point between 0 and pi. A convenient one is pi over 2. So x of 0 is 2 times sine of 0, which is 0. And y of 0 is 3 times cosine of 0. Cosine of 0 is 1, so that's 3 times 1, which is 3. So that's telling us that we're at this location, x of t, y of t equals 0, 3. At time t equals 0, we are here. And x is 0, y is 3. So at t equals 0, we start there. Okay, question becomes, well, where am I at t equals pi over 2? Well, just plug it in. We're going to be at 2 sine of pi over 2 and 3 cosine of pi over 2. That's our x-coordinate and that's our y-coordinate. Sine of pi over 2 is 1. So we get 2 times 1, which is 2. Cosine of pi over 2 is 0. So we're at this location now, when x equals 2, y equals 0. And that's at t equals pi over 2. So we can think of that as pi over 2 seconds later, we're over here. It looks like we're going this way. But just to be sure, let's plug in pi. This actually doesn't guarantee anything, but it indicates it's probably the way it's going. When you substitute in pi, sine of pi is 0, cosine of pi is negative 1, so you have 3 times negative 1, which is negative 3. We're at this point, 0, negative 3, down here. So that's at t equals pi, and that's all we get. The set of parametric equations was given, and we were told that it defines some curve for t between 0 and pi. So we don't get the whole ellipse, we just get this half of the ellipse, and it's traced out this way. As t increases, we go from the top to the bottom. I'm going to highlight that just to make it very clear. R of t is not the whole ellipse. R of t is this part of the ellipse, or the curve generated by R of t is this part of the ellipse. Okay, so I think we're going to stop here for this video. So far we've talked about vector valued functions and what they are, and we've talked about plane curves and how they can be given by x of t, y of t, and then how we can sketch them. In the next video we'll look at graphing space curves, and we'll talk about issues like domain and smoothness and limits. Maybe the next video or two after that.